Have you ever just gone outside on a really clear night, looked up, and just been totally blown away? I mean, those thousands of little twinkling lights have fascinated people forever. We've used them to find our way, to tell stories, to mark the seasons. But what are they? What are we actually looking at?
Yeah, what are those little dots really? Well, in this explainer, we're going to pull back the curtain on the cosmos and tell the incredible life story of a star, from the moment it's born from dust to its absolutely explosive death.
So, when you get right down to it, a star is a pretty simple idea, but it's also unbelievably powerful. It's this giant ball of super hot gas, so huge that its own gravity is constantly trying to crush it into a tiny point. So what stops it? Well, there's a ridiculously powerful engine in its core called nuclear fusion. That's what blasts out all the energy we see as starlight.
All right, so where do these cosmic powerhouses even come from? I mean, they don't just pop into existence out of nowhere. Believe it or not, their story begins in some of the coldest, darkest, most seemingly empty parts of the entire universe. So let's see how they go from just dust to a fusion-powered giant. Stars are born together, kind of like siblings, inside these massive, swirling clouds of gas and dust. We call them molecular clouds, or, a bit more poetically, stellar nurseries. And when I say massive, I mean it. These things can be hundreds of light years across and have enough raw material to build millions of stars like our sun. So here's how it goes down. Something gives the cloud a little push, maybe a shockwave from a nearby exploding star. A little piece of it starts to clump together. As it gets bigger, its gravity gets stronger, and it pulls in even more gas and dust, collapsing in on itself. All that pressure starts generating heat, and the center begins to glow. That's a baby star, a protostar. It spends the next few million years just getting bigger and bigger, hotter and hotter, until the core gets so incredibly hot and dense that, bam! Nuclear fusion kicks in. Hydrogen atoms start smashing together to make helium, releasing an insane amount of energy. And right there, in that moment, a star is born. Okay, so the nuclear furnace is officially lit. Now the star settles in for the long haul. This is the longest, most stable part of its life, and we call it the main sequence. In fact, a star like our sun will spend about 90% of its entire life right here, just steadily burning through its hydrogen fuel. You can think of a star's whole life as this constant, epic battle. It's a cosmic tug of war. On one side, you've got gravity. It's this relentless, crushing force, always trying to squeeze the star down to nothing. But fighting back from the inside is fusion, this incredible outward pressure from the super hot core, always pushing out. And when those two forces are perfectly matched, that's a state that scientists call hydrostatic equilibrium. It's this beautiful, perfect balance, a cosmic dance between crush and push. And it's this exact balance that lets our sun shine so steadily, day in and day out, for billions of years. So what decides what a star is going to be like? How hot is it? What color is it? How long does it live? It all comes down to one single thing it's born with: its mass. That's it. Mass is the master variable. It literally determines everything about a star's life and its death.
And just look at how much of a difference it makes. A little low-mass star, a red dwarf, is kind of cool and red. It just sips its fuel so slowly it can live for trillions of years. That's way longer than the universe has even been around. Then you've got stars like our sun, in the middle. Hotter, more yellow, with a respectable lifespan of about 10 billion years. But then you have the heavyweights, the big blue giants. They are so hot and so massive, they have to burn through their fuel at a truly insane rate just to stay alive. They live for only a few million years. They really do live fast and die young. But nothing lasts forever. Eventually, that main fuel source, hydrogen in the core, it starts to run out. And when that happens, the outward push from fusion gets weaker, and that cosmic battle, well, gravity starts to win. The core begins to collapse, and that's the beginning of the end. And guess what? Just like it did for its life, mass decides how the star is going to die. When that core starts to collapse, the star comes to a fork in the road. Low and medium mass stars get to go out pretty gracefully. But the high mass stars? Oh, they're headed for a truly spectacular, violent end. Let's take a star like our sun. As its core collapses, it actually gets hot enough to start burning the leftover helium ash, turning it into carbon. This new burst of energy makes the star's outer layers puff up, turning it into a massive red giant. Eventually, those outer layers just kind of drift off into space, forming this gorgeous glowing structure we call a planetary nebula. And what's left behind? Just the hot, super dense core, a white dwarf, about the size of Earth, that will just sit there and cool off for the rest of time.
For the really massive stars, though, it's a totally different story. They don't just stop at turning helium into carbon. Their gravity is so intense, it just keeps crushing the core, getting it hotter and hotter, and it starts fusing heavier and heavier elements. It creates these shells, like an onion, each layer burning a different element.
And this is where things just get frantic. I mean, look at this timeline. It burned hydrogen for millions of years, helium for 500,000. But then look at the end. Carbon burns for 600 years, neon for about a year, and the very last fuel, silicon, that lasts for about a day. The star is in a desperate panic, running out of options and running out of time.
And then it hits a wall, a hard stop. That wall is iron. See, for every other element, fusing it released energy. But with iron, it's the opposite. It actually takes energy. So the fusion engine that's been holding the star up for millions of years just switches off. The outward pressure vanishes in an instant, and gravity wins, catastrophically. The whole iron core collapses on itself in less than a second. It gets squeezed so hard that it actually bounces back. And that rebound creates one of the most powerful shock waves in the entire universe, which just rips through the rest of the star. Just try to get your head around this. The temperature in that collapsing core hits over 100 billion degrees. That is just, it's almost impossible to imagine. The physics happening here are some of the most extreme in the cosmos. And the result is a supernova. The star tears itself apart in an explosion so ridiculously bright that for a few days, it can actually outshine its entire galaxy of hundreds of billions of other stars. What's left of the core gets crushed into either a tiny city-sized object called a neutron star, or, if the star was big enough, it collapses all the way down into a black hole. Now, you'd think an explosion like that is the end of the story, but it's not. In a way, it's the most important part. It's a new beginning. Let's get to our final section and see how this all connects, well, directly back to us. See, whether it's the gentle puff of a planetary nebula or the unbelievable violence of a supernova, the star's death throws all those heavy elements it created, the carbon, the oxygen, the iron, out into space. This stuff then mixes in with those big molecular clouds, enriching them with the raw materials needed for the next generation of stars and, crucially, for planets. Okay, so let's boil all that down. Here are the 5 big takeaways. 1. Stars are born in huge clouds of gas and dust. 2. Their whole life is a tug-of-war between gravity and fusion. 3. Mass is everything. It decides the star's entire fate. 4. Small stars die quietly, massive stars go out with a bang. And 5. Maybe the most important one, stars are cosmic factories that create the heavy elements needed for planets and for life. And that brings us to the most amazing part of this whole story. When the universe began, there was basically just hydrogen and helium. Every other element, every atom of carbon in your body, the calcium in your bones, the iron in your blood, all of it was forged inside a star that lived and died billions of years ago. We are, quite literally, made of stardust. So the next time you look up at the night sky, just remember, you're looking at your own cosmic family tree. The only question left is, what will you do with your stardust?